Hello everyone. In today's lecture we'll start discussing about the memory hierarchy. This is a bigger subject, bigger than one could possibly fit into a single class, so I decided to divide it into two separate classes. In the first class, in today's class, we will be introducing memory hierarchy and then focus on caches, small memory units that allow fast and easy access to data and instructions. And in the next class, hopefully, we will be focusing on the virtual memory basics and discuss and compare it to the general caching idea. Here is two pictures showing the memory system for a CPU using hierarchical architecture and without it. As we go outward from CPU, the memory system becomes slower, yet it becomes more capacious. In other words, the technology behind it make it store more and more data. You can add more devices to this hierarchy to complete the whole picture. For example, we can attach a tape system to talk to HDD in this hierarchy. On the other hand, without the hierarchy, we would have HDDs directly connected to CPU for data storage. And there would be a variety of problems associated with no hierarchy model, as we will discuss more about it moving forward. But this is actually the basic subject matter of this class today that we're proposing to cover. So in order to understand the advantages of having hierarchy in a memory system, we should look at the frequency of accesses made to each block of the memory system when running a typical program. Here I'm giving you an example where frequency of accesses are 99.9% for cache and 0.1% for main memory, and very rarely for SSD and HDD. You can also see the access times for each of these memory units given at the top. If you compare two memory systems, one with hierarchy and one without it, you will realize that with hierarchy, most of the time it takes 1 nanosecond, maybe on average 2 nanoseconds overall, to get the data into the CPU registers. And in that case, CPU does not halt much. Yet without hierarchy, it may take seconds to get to the data, and CPU halts frequently, which leads to inefficient use of resources. Here is the ideal picture. This picture shows an ideal memory system and its connection to the CPU. We would expect a very large and very fast memory system to respond to CPU requests in a timely manner, right? If you remember our previous discussions about CPU and memory system and the gap, the speed gap between CPU and memory, this is the ideal scenario where it will respond to our request. Fast reads and writes, for example, coming from CPU. However, there is no such a practical memory system in the real world, unfortunately. Memory hierarchy is essential to achieving high speed, large memory, and low cost. Again, the overall purpose of the cache hierarchy is to bridge the speed gap between the CPU cycle time, less than a nanosecond, for example, and the access time of primary memory, which is tens of nanoseconds for commodity DRAMs. The success of memory hierarchy is based on the access frequencies. These access frequencies must be accurate enough so that we will gain some performance advantage. This assumption comes from something called locality or reference locality. There are two types of locality. It may refer to the relative times at which instructions and operands are accessed, which is called temporal locality. It could alternatively refer to relative memory locations at which instructions or operands reside in main memory. This locality is called spatial locality. Let us remember some of the basic programming tools like looping. Looping means accessing the same set of instructions again and again until the loop condition is no longer satisfied. Also, instructions are most probably placed in close proximity in memory in sequential order, which provides spatial locality as well. You can arrive at the same conclusion if data was accessed to, for instance, one of the well-known examples could be accessing arrays, where the entries are stored in a sequential order in consecutive memory locations. The concept of locality is very essential to the success of caching and building virtual memories. So we start our discussion on cache memory by giving an example of direct map caches. Cache is usually manufactured using SRAMs, static RAMs, and faster, which are faster than DRAM main memory element, right? As you can see, caching is acting just like the main memory, except that it does not have enough space to hold everything in the memory, in the main memory. Here, the main memory is assumed to have 32-bit word size, and it's also byte addressable, and hence the last 2 bits can be assumed to be 0 when we address words in the main memory. We partition the address line into 3 fields: tag, index, and byte. Index field is selected to be second, third, and fourth bits of the address due to special locality. The index tells us where in the cache is the data stored. The tag, which is the first 5 bits of the full address, is also stored as part of the cache. This way, from any cache location, we can infer the full main memory address, so the data at that particular location can be transferred to the data portion of the cache and stored there for CPU access. If that data is asked or requested, then the instruction or the user data is directly fetched from cache to the bus or the instruction register. This is called cache hit. If what CPU asking is not in the cache or is not found in the cache controller must notify main memory for the data requested. This is called cache miss, and it takes some time to bring the data to the cache and provide it to CPU use. The particular association of cache address and main memory here presented does not always provide the best desirable solution. For example, suppose that the main memory contains both instructions as well as data at locations where the cache index bits are identical. If the data is frequently used, the data will be in the cache at the beginning. Then when the instruction is fetched, the data will be evicted, and in that location the instruction will be stored. When the same data is requested by the CPU in the next couple of clock cycles, it will result in cache miss. And in a loop, this will repeat many times, leading to many cache misses and degraded performance. So the fixed mapping can be harmful, and instead a pseudo-random mapping could be used through hardware random number generators. In order to track the memory address accurately, the tag becomes 8 bits long, and there will be no index fields. Such a cache is known as fully associative cache. This cache would minimize the chances of the problem we just talked about happening at the cost of storing more metadata, for example, larger tag fields. As you can see, fully associating each memory location with any cache address leads to extra space and logic, such as increased cache size, as well as matching circuits, comparators in our case, to check on more bits whether the tags are the same. So as can be seen, both of the mappings we covered so far has their own pros and cons. As the tag size increases, the cost associated with implementing the cache increases. Yet smaller tag size causes unnecessary cache misses, more frequently than otherwise, as we have seen in direct mapped caches. So a compromise between these two extremes might be needed that solves, or hopefully will solve, the trade-off well. The solution is to have S different sets. In other words, we divide the cache address space line into equal size sets, and for each set we apply direct mapping. Therefore, the index size and the number of sets can be jointly determined depending on the cost that can be tolerated and required performance, of course. An example is shown in this slide for two-way set-associative cache, where the rows are determined by the index of the main memory address. So there are two locations in cache once the index is fixed. If both are occupied for a given memory address, then one of them must be replaced. With this setting, we need only 2 matching circuits, not 8, which would provide more flexibility in terms of logic needed to implement the cache. Here is the partial hardware for set-associative cache. As you can see, there are only 2 matching circuits, 2 sets for both tags and data. The rest of the logic is pretty easy and neat, so I'll basically leave it to you to understand the details of this logic block diagram. So when there is a cache miss, there is usually more than one word fetched at a time. This is due to our previous discussion of spatial locality concept. The bulk of memory words that are fetched into the cache is called a line. The whole line is fetched fetched when data or instructions are requested from the main memory. This also changes the makeup of the address fields. More specifically, it adds extra word field into the address and the cache separates. Let us set the line length to be 4 words, so the word field consists of 2 bits. Index field is also set to be 2 bits. Using our previous example, this would imply for a two-way set-associated cache, the cache is now capable of holding 32 words at the same time. Here is what we have using fetching lines instead of single words. One of the design decisions that cache designer ought to make is the bus size that fetches the line from memory to the cache. If it's, for our example, smaller than 128 bits wide, then multiple reads from memory can be required. Another decision that has to be made is the line size. How many words must jointly be brought into the cache or be evicted from the cache? Having larger line size probably badly will affect the cost and performance metrics, whereas the larger lines are needed by the special locality of reference. Latest modern DRAMs allow large lines to be read and written without dramatic extra costs, so they are matching well the needs for transferring cache lines. So far, we have discussed and focused on reading lines from cache, and if absent, loading it from the memory. But how about the result of an operation that needs to be written to the memory? There are basically 2 methods. The first one is called write-through caching or write-through cache, in which the result is directly written to memory. This can be slow because of the memory accesses, as you might guess. Most of the modern systems use buffers to expedite this process. If there is a cache hit, the result gets written into the cache also. If not, the cache is untouched. The second method is called write-back cache. In this method, CPU attempts writing to cache only. If misses it, it gets written to the memory. The main idea behind write-back caching is to write at the writing speed of the cache whenever there is a cache hit. And if cache miss happens, we bring all the line containing the word to be written into the cache, allowing to reduce write cache misses due to the reference or locality. This is also known as write allocate method. The disadvantage of write-back caching is that in case of a cache hit, the corresponding memory location is stale and problematic for other CPU cores or I/O processors. We will discuss I/O processors in the future. But there are just extra processors or extra CPUs. They may be accessing the same memory location because they will not be able to access the updated data or operand in the memory. So it will basically reach at fetching in the stale data or stale instruction. Plus, if cache dies off, the data will be lost in write-back cache. In order to provide access to 2 distinct addresses in a single clock cycle, a parallel access, you will need separate caches for instructions and data. Having separate caches will put different design challenges and perhaps less stringent conditions because the demands on each of these caches are typically less than those on a single cache. For example, in order to keep cache misses as well as the implementation costs at a reasonable level, while a single cache may require a 4-way set-associative structure, in a separate case, an instruction cache may need only direct mapping, and a data cache may need only a 2-way set-associative cache structure. On the other hand, it's possible to extend the depth of the memory hierarchy by placing faster and smaller caches close to the CPU and secondary and slower caches underneath to support that fast cache. These might be 2-level, 3-level, even 4-level caches, and historically they are called L1, L2, and L3 caches, where L1 is the fastest and also the smallest and closest one to the CPU. L1 cache is customarily built into the CPU chip, alleviating the need for extra pins and inter-IC communications. Since L2 and L3 caches are used if the data or instructions cannot be found in L1, these caches are at different levels of hierarchy will have different access patterns, and therefore that will imply distinct design challenges. So in this class, we covered basics of memory hierarchy, ideal memory system in an attempt to close the speed gap between CPU and memory integrated circuits. One of the brilliant ideas of computer science and architecture was the invention of caches. Caches allowed faster access to the data at the cost of occupying more space and small capacity offerings. Next class, we will be focusing more on the capacity aspects of caching and look at the idea of virtual memory, which have been rooted at early 60s and are still being used in modern systems. Please feel free to drop any questions you might have about today's lecture into my email box, and I'll be more than happy to help you with your questions. Thanks a lot.